In this tutorial, we'll look at I2C protocol, which stands for Integrated Circuits Communication Protocol. It's basically a two-wire interface, also known as TWI. Now this you could find it on a whole lot of chips, ICs, on ROMs, LCDs, and ADCs, and also on microcontrollers. So this protocol just uses two wires to communicate between ICs, and of course we need a common ground between all of them. Now let us go ahead and look at the basics of these. So as said earlier, so the I2C has just two lines. So one of them, it's called the clock. So if you could remember a discussion on UART, so it was asynchronous, meaning there's no common clock. But in I2C we have one line for a clock, and there's one more line, and this is called the data line, so SDA. Now, so since this is clock, there should be the one more line, obviously should be a data line. This is called the I2C bus, and all the devices, these share these two lines. So say we have a device here, say we have a microcontroller here, and we have whole other peripheral devices, like say if you heard about an RTC which works on I2C, so it could be RTC TS1307. Then there are a whole series of ROM ICs, the EEPROMs, which use this protocol. Then there are ADCs and displays and whatnot. So there are whole list of bunch of devices that work on this particular protocol. So now at any given point in time, the one device, it's called the master. So, and all the other devices, all the other devices here, these are called the slave. And since as you could clearly see, there is only one line, and there could be only one device transmitting and receiving data. So only one device transmitting at a time, and more than one device is receiving. So since the communication needs to be bidirectional, what I mean is the microcontroller needs to speak to a specific device, say EEPROM or RTC. There is an addressing mechanism for all of the devices. Now before you go ahead and discuss all of that, so say we have the data line which is connected to all of this. So data line is connected to all of these devices, and then we have a clock, and the clock basically is generated by the master. So at one point in time, there is only one master controlling the bus, and the clock is generated by the master, and it is received by all the slaves. Right. So and one more important thing about this protocol is the standard specifies the SCL and SDA pins on the devices to be open drain. So this is SDA pin on the microcontroller, and this is SCL pin on the microcontroller. So both these pins have internal structure, something of this kind. So they have, say, an FET, and this FET is grounded. This is some control inside, but what you could see is this particular line, in this case SCL, it is not connected anywhere. It directly goes to SCL of other devices. Now what that means is this is normally open, or it is called open drain. So we can have a stable low voltage, so this can be at ground, but when the pin is not at ground, it is floating. So for this protocol to work, we should have external pull-up resistors. So this should be connected to VCC, and both the SCL and the STA lines, these should be connected to it. So these are two pull-up resistors. Let's say this one more, and this goes to the other line. Now, since you could understand the why we require a pull-up, because if it is not grounded, the pin is floating and we do not have a stable voltage on the line. And also remember that when the bus is not operating, both the lines are pulled high, and that is where we would start the discussion on communication width. Now, what happens with this is, since there is only two lines on which the communication needs to happen, there are specific timings or specific combination of these two signals are generated in order to transfer data over devices. And there's one more point to be mentioned here. So there could be more than one master devices, and there's a process called the bus arbitration, which determines which master has control over the bus. So in this tutorial, we'll confine our discussion to a single master, and we would also assume that all the devices are operating on 5 volts. So there are instances where you could have a 3.3 volts device interfaced to a bus which is working on 5 volts. In such cases, a level shifter is recommended. Now let us go ahead and look at the what are the protocol considerations that are done in order to transfer data. Since we only have 2 lines and these are pulled high initially, so let us say that this is our clock line and this is high, and this is say our low level, and there is also a data line. So say this is the data line, and this too is high. So this is high level and this is low level. This is high level for this, and this is low level. Right, so say this is our clock line, the SCL, and this is the data line, STA. Now for the communication protocol, to begin, we define something called a start bit. Now the start bit is, when in the beginning the clock would always be high. So if the data line goes from high to low, right? So if the data line goes from high to low, so this transition, this transition when the clock is high and the data line going low, this is called the start condition. So this particular transition here, this is called the start, and it is denoted by S. Now similarly, say we want to stop the communication on the bus, so we need to pull the clock line high, and so the data line it goes from being low to high. So if it makes a transition from low to high, so this condition, it's called the stop condition. So this is stop condition, and it's usually denoted by P. Now as you could see, since the start and the stop conditions are defined when the clock is high, all the data transitions should happen when the clock is low. Now let me just explain that in a little detail here. Now say we want to transfer a byte of data. Say we want to transfer 0xAA or 10101010. So alternatively ones and zeros. Now the clock line, it basically what it does is it simply generates a clock pulse. So say for instance we have a clock pulse. We'll discuss about the speed and all the other characters. So say this is our clock line. So this is the low period, this is the high, and then it follows with the low and high. So we have this clock period here, and eventually it goes high. Okay, so this is the clock period. Now this is one clock cycle, as you should be knowing, right? So this is one clock cycle. Now what the protocol says is, for the receiving device to know whether a 1 is transmitted on the data line or 0 is transmitted on the data line, all the transitions from 0 to 1 or 1 to 0, they should happen only when the clock is low, because we know that the start and stop conditions, these are defined when the clock is high. So all the data transitions should happen only when the clock is low, so that the receiving device could sample its pin when the clock is high. So when the clock is high, the data would be stable when we have transitions only on low clock pulse. Since we have 3 clock pulses here, let us say we want to transmit the 3 bits, and there is one more important point to note here. The MSB goes out first. Okay, so if you want to transfer 8-bit data on this, the first bit that goes off is an MSB. So let's say we want to transmit a 0. Now, as said earlier, the transition should occur only when the clock line is low. So say this is low and it continues to be low since we want to transmit a 0. Now it should not change when it is high, so it should remain low. Now next we want to transmit a 1, and for this the transition should only occur when it is low. So what happens is it goes high here, and then it remains high for the entire time this is high. So now to send a 0 on the next clock pulse, the transition should occur only when the clock is low. So it comes back and then it continues. Now what you could observe is when the clock is high here, so when the clock is high, the data line is always stable. So here we have a 0, then for the next, when the clock is high, for this period this is 1, so this is 0 and this is 1. So now this is what makes this protocol work efficiently. So the point here is the start and the stop conditions are defined when the clock is high, and all the data transitions from 0 to 1 or 1 to 0, they happen when the clock is low. So when the clock is high, you will have stable values on the data line. So the clock is high here and we have stable 0. So clock is high here and we have stable 1. So this is called data validity, and for data to be valid, it needs to change only when the clock is low. So here we see, so the data has changed from 0 to 1 when the clock is low, and is stable all the time when the clock is high, so that the receiving device, which is on the other end, say the master is transmitting or receiving, so the receiving device will have a stable value when the clock is high. So this condition is called the the start, this condition is the stop, and these are the bit transfers. Now let us go ahead and look at the data format and how the actual data is transmitted. Now the communication starts with sending a start byte, a start condition, which we have discussed. So we do a yes, then what is done usually is a device address is sent, and the device address is 8-bit. Out of the the device address is 7-bit, and all the data transfers that we'll be discussing are 8 bytes. So the 7-bit plus 1 bit, which is called the read write, is transmitted first, and this is called the start byte. So this was the start condition, and this is the first byte which is sent. This is called the start byte. So this is 7-bit. The 7-bit is address, and this one more bit which is read/write bar. Now since master is sending it, so what it means is the 7-bit address is the actual slave address that we are transmitting it to. Now since if we look at the picture, so say the microcontroller wants to communicate with an RTC, so it needs to send its address first. Now so that is the address it sends, and it also tells whether it wants to transmit or receive. So if the read write pin, so this is 1 bit, so if this bit, if it is 0, then the microcontroller wants to write, or the master wants to write, and if this is 1, then the master wants to read from the slave device. So we have a start condition, we have a stop, we have a start byte, and then we continuously send bytes of data, and the communication ends with stop condition. So stop condition is the P. Now we have left out various points here, but these are good enough if you want to work with a I2C device which has a 7-bit address and transfers 1 byte at a time. So there are even devices with 10-bit address lines, and there is one more thing that we missed out. So whenever we send a byte of data, okay, so there's two more conditions that we need to discuss. So if we go back to the previous slide, yes, so this is the start condition, this is the stop condition, and there is whenever we do a data transfer, whenever we send a byte, whenever the master transmits a byte to receiver, there is an acknowledgement back from the receiver. And so the acknowledgement basically is, again, since we transfer 1 byte or 8 bytes at a time, the 9th clock cycle is called the acknowledgement. So now it could be positive or it could be negative. So if the receiver wants to give a positive acknowledgement, and say we have so if it wants to give a positive acknowledgement, what it does is, say this is our clock. So what it does is, and this is the 9th clock, and 8 bytes have already been transferred. So what it does is, so this is the clock line. So what it does is, it holds the data line low. So this indicates, since any of the device could pull the data line low, the slave pulls it low to indicate that the previous 8 bits or a byte was successfully transferred, and this is called the positive acknowledgement or ACK. There could be a negative acknowledgement in which the slave or the receiving device, it makes the line high, it makes the data line high, or simply releases the data line. So what happens here is, this is called as NACK, and it could be due to several reasons. The device is not ready to accept instructions or any other reason that the communication was not complete. So in this situation, the master device sends a start condition again, and this is called the repeat start, or it could abort the operation itself. So so basically we have the start condition, the stop condition, the repeat start, the positive acknowledgement and negative acknowledgement. So these are the basic things that you need to know before interfacing I2C devices. Now if you're using a device with 3.3 volts, you need level converters, and if you need, if the device uses a 10-bit address instead of 8-bit or 7-bit, then we need to consider a few more things. But for now, if you're using a 5-volt device working on 8-bit addresses, this should be sufficient. Thank you for watching, and in the next tutorials we'll interface it with the microcontroller and I2C device.